All right. So this is where things get weird. Very quickly, I promised sort of 14 or 15 just responses to fine-tuning. I'll quickly run through those. There's one or maybe two that I want to have a quick look at just before I move on to the multiverse. So here's the first 8. So we can discuss it. I mean, we have the rest of the week to discuss these. So you could say it's just a coincidence. Who cares? You could say, hang on a second. We've only observed one universe, right? So the probability of a life-permitting universe seems to be 1 out of 1 for all we've observed. Number 3, low probability events happen all the time. People win the lottery, stuff like that. Number 4, the Anthropic Principle, which I'll discuss in more detail in a second. Number 5, evolution will always find a way. I think from what I've told you, that's just obviously false, right? People say that. Biologists tend to say that. But if the universe recollapses in 10 seconds, go evolution. 6, there could be other forms of life. I'll have a few things to say about that. 7, this universe is just as unlikely as any other universe. I think the best answer to that is if I was playing poker and every time I dealt myself a hand, I got a royal flush, and you said you're cheating, and I said, hey, 5 royal flushes in a row is just as unlikely as any other set of 5 hands. I think that one falls apart. 8, how do we really know what would happen in these other universes? Go do the experiment. We can't do an experiment, it's another universe, but we can do theoretical physics. We obviously can't do observational/experimental physics, but the question is what would happen, and so it's a theoretical argument anyway. Moving on. How can the universe be fine-tuned when so much of it is inhospitable to life? I think there's a very good answer for this one, actually. If you want the universe to be long-lived so that stars have enough time to burn into fuels, you need to make it quite big. So there's a relationship between how big and sort of spacious the universe is and how long it lasts. So that I think we understand quite well. Again, we can discuss these over beer. 10, life chauvinism. You just assume that universe has a purpose, that life is special. Well, not in a fine-tuning case, maybe in a fine-tuning argument for the existence of God, but we'll move on to that more later. 11, fine-tuning has been disproved by ... That one is an internet one. And no more needs to be said. 12, deeper physical laws will explain the values of the constants. I'll have more to say about this when I talk about inflation in a minute. 13 is the multiverse coming up, and 14 is what we're all here for. Let me have a quick, just quickly talk about the Anthropic Principle. I prefer to think of the Anthropic Principle as a type of selection effect. Now, if you are an observational astronomer, or if you have aspirations in that field, you will spend half of your life worrying about selection effects. So let me give you an example. In the early days of cosmology, sort of 50s and 60s, maybe 70s, there were 2 competing models. There was the Big Bang model and there was the steady state model. The idea of I told you the history of the Big Bang model, that's what I've given you. The steady state model was that on average the universe doesn't change with time, it's expanding, but new matter is created to sort of fill the void. And so on average the universe doesn't change with time. Now, one way that you can test that is you can go look in the very distant universe. Because light takes a certain amount of time to travel across the universe to us, you're seeing galaxies as they were in the past. So, I think the record for the furthest thing we've seen in the universe is about like 1 billion years after the Big Bang, so like 12 billion years ago. So you really are seeing a long way into the past. And certainly the cosmic microwave background is about 300,000 years after the Big Bang. So that is really in the past. The thing you can do is go look for galaxies way out in the universe and see what their properties are, and then have a look at local galaxies and see what their properties are. And if they are systematically different, then the universe must have changed between then and now. If galaxies like that were all pink and the ones all today are all blue, then there's something in the universe has changed over that amount of time, and so the steady state model must be wrong because the universe has changed with time. Okay? So you go do these observations. Now, this axis is distance, well, related to distance, something called the distance modulus. It won't really matter. The points are what you're after. This axis is intrinsic luminosity, related to the intrinsic luminosity. It is how much energy you're putting out per second, that the galaxy is putting out per second. Now, question for the class. These are all the points, never mind the line, these are all the points that we have observed. All right, so all of these points are a galaxy where we've seen this galaxy is at this distance, and it has this luminosity. What should we conclude from this plot? I'm going to start pointing. Someone? Anyone? Wrong! Yes! Someone had to fall for it. Exactly. Thank you very much. Okay. Why? The reason why is actually this line. The further away something is, the harder it is to see. So the brighter it has to be before you see it. Okay? This line is the flux limit, which is how bright something has to be before we're sure we see something rather than just the noise in our detector. Even if there were galaxies down here, we wouldn't see them. So all you're seeing is, imagine if this whole region here was just filled with points, you would still see this kind of trend just because you can't see these points. Okay? The reason you don't see many points up here is because the closer you look, the smaller the volume you're looking at. So most of the volume of a sphere is near its edge. I think most people know that. Okay? What that means is you can explain all the features of this plot just by a selection effect, that we're not taking a random sample of the galaxies in the distant universe, we're only getting the brightest ones. Okay? So that is the core of any sort of selection effect. Now, they all sound tautological, okay? This selection effect is, we can only see it if we can see it, right? So I think the best way to say the anthropic principle is quite similar. You know, if observers observe anything, they observe a universe which allows observers. It's tautological, but it's still it's not trivial. So I think that is a good way of thinking about the anthropic principle, and there'll be more of that when we start thinking about the multiverse. The other one I wanted to look at was, where are we? 6. There could be other forms of life. Now, this is a good point. Remember I talked about silicon. So let's just think about silicon-based life. Suppose that you've mapped out in your parameter space all the regions where carbon-based life will form. Okay? Silicon-based life is inferior, so it would need more specialized conditions to form, right? If you have to get things just right for carbon-based life, silicon's going to be even harder. So if these were all the universes that could support carbon-based life, the ones that could support silicon-based life would be even smaller. They'd be, okay? Now, if you have a universe which can make silicon, it could probably make carbon as well. So what that says is, if you've got a universe which is suitable for carbon-based life, most of those will also be okay for silicon-based life. So if this is, we sort of put a pimple on the side of the life-permitting region. It just doesn't make much of a difference. So could there be other forms of life other than ours that are possible? Yes, but I mean, I think it's plausible they would be just as fine-tuned as ours. And certainly, remember that I said chemistry isn't fine-tuned. Chemistry is actually quite general, quite robust. So the fact that you need carbon is actually quite a general statement across possible universes. All right. Let's.
Can I just clarify?
Yeah.
So the point is not just that other kinds of life would also be fine-tuned, but rather this junction of all of them would still be fine-tuned, right?
Sorry, say that again.
So it's not, so say there are 15 different ways to have life.
Yeah.
The point isn't that just each of these would itself be fine-tuned, but that the disjunction of all 15 of them.
The union of all 15, yeah.
Yeah, that's right.
Yeah, so if you want to calculate the life permitting region, you need to take into account all the forms. If they're all small, then you're not making much of
well, unless it's a whole lot.
a gate. Well, yeah, granted. Okay, the multiverse. I think this is, at a first level, this is a very natural response to something that looks unlikely. Okay, so let me give an example. Now, that's my daughter. Now, you might be thinking she's pretty cute, and you'd be right. Okay, you might be looking at me thinking she must get it from her mother. You're also correct. You might be thinking she's very photogenic, that she takes a good photograph. Now, that might be true. But perhaps we've taken so many photos of this kid that eventually we had to get one right. Okay? That's a personal favorite there. Okay? So after 10 billion photos that look like this, we eventually get one that looks like this. Yeah? Why do people win the lottery? Well, because lots of people buy different tickets. Okay, you can explain low probability events by having lots of different goes at it. Incidentally, I keep hearing people say in this context, well, someone has to win the lottery. That's not true. No one has to win the lottery. Okay, if no one gets the right ticket, it jackpots. It can jackpot forever. Sorry, that's a minor point that just keeps annoying me every time. There is a tension here, and it's actually quite an old problem in physics between what features that we see around us in the world are just kind of accidents of the way, of the initial conditions and of the way we set up, and what are actually sort of fundamental features that we should explain. A great example of this is Kepler's laws. So Kepler was a great astronomer who finally, after thousands of years, discovered the three laws of planetary motion. So if you put these three laws into action, you calculate the orbits of the planets much better than the old Ptolemaic system where you had a perfect circle and then you had the epicycles going around. The three laws are the orbit of every planet is an ellipse. A line joining a planet and the sun sweeps out equal areas in equal times, and the square of the orbital period is directly proportional to the cube of the semi-major axis of its orbit. Basically, how far from the sun you want your planet to orbit determines how long the year is before it gets back to where it started. Kepler wanted more, okay? The third law says as a relationship between where the planet orbits and how long it takes to orbit the sun. What Kepler wanted to do was to explain the orbits themselves. Why do the planets orbit exactly where they are? And he went through all kinds of ideas. So there were ideas related to maybe the orbits in the right way form some sort of musical scale. Maybe the orbits are related to the Platonic solids. So the polyhedrons where all the sides are the same, like a cube. Each side of a cube is a square, and a tetrahedron, and there's three others. That obviously doesn't work because there are more than 5 planets. There was all sorts of weird ideas for how to explain, but actually, so what Kepler wanted was a fundamental, something really deep in physics, whereas actually the modern view of planet formation is that where the planets orbit is really just sort of an accident of history. They happen to, here or there. It was just sort of minor particle fluctuations here and there puts it where the planets where they are. There's nothing fundamental. So that tension here between explaining things in terms of a fundamental unchanging law on the one hand and explaining things as just the product of your environment, which could have been different from here to there, is very much a tension in fine-tuning. Should we be looking for deeper laws, or should we be going for basically the multiverse idea? Let's do a test case, and it's quite a useful test case. It's cosmic inflation. I showed this plot before. There are a couple of not problems with standard cosmology as I told to you, but just sort of things that make us a bit uncomfortable. I'll explain what I mean by that. A lot of the features in the model of the universe that I told you about have to be put in as initial conditions. The fact that the universe is expanding is simply because it started expanding. The fact that the universe is very uniform and isotropic is because it started uniform and isotropic. Why does the universe have the sort of, density fluctuations that will go on to make stars and planets and galaxies? Because it started with those. There's a lot that went into initial conditions. Now, that's not so much a problem. You have to face up to initial conditions at some stage, even if the universe is infinitely old, because you still have initial conditions, but at negative infinity. They were just a bit awkward. One of them is called the flatness problem. Okay, the green line. When omega matter equals 1, so a specific density in the universe, that means that the spatial geometry of the universe is flat. Now, the problem with this point is this is an unstable equilibrium. Remember the ball on top of the thing? So if the slightest nudge one way and it rolls off one way, and the slightest nudge the other way. So if you start the universe, go back to those initial conditions, if it's exactly flat, it will stay flat. So it will stay with omega equals 1. Slightly off to one side, and it will very rapidly. So if it's slightly more, it will very rapidly become a lot more. If it's slightly less, it will very rapidly drop to 0. So it's an unstable point. And actually, if you want a universe now, which is close to flat, which ours is, it needs to be, at nuclear synthesis, just sort of 3 minutes after the Big Bang, it needs to be correct to within 1 part in 10 to the 16, so 1 plus or minus 10 to the minus 16. And if you can go all the way back to the Planck time, before which we can't really predict what's going on, then that number becomes 1 part in 10 to the 55. Now that's just a bit awkward. There's an anthropic issue here as well. Galaxy formation depends on omega, and you need omega to be just about equal to 1 at the present day. If it's too much less than galaxy, there's not enough matter in the universe for it all to clump together. And if there's too much more, then this happens, and no structure forms because the universe just big crunches very quickly. This isn't a typical scientific problem. Usually when you have a scientific problem, what you're talking about is there's your model and there's data and there's something that's not matching up. This is not that sort of problem. This is just our model seems to be a very sensitive function of the assumptions. The success of our model, its ability to predict the universe, is a very sensitive function of what assumptions we have to make about initial conditions, which is it's just awkward. There's another, I think, more awkward problem. This is just a representation of space and time, okay? So this is a space axis and, say, time axis. So this point here would be a particular place and time, okay? These horizontal lines define the light cone. So light obviously moves through space and time. So if light was emitted here, going that way, later on it would be at a different place, and if you wait a bit later it will be here, and then it will go out that way. The reason why this is important is because nothing can travel faster than the speed of light. What that means is all of the causal processes that determine what goes on here are in this causal past light cone. Something out here, elsewhere in the universe, it doesn't matter what happens out here, it can't send a signal fast enough to affect anything that happens there. So the light cone constrains causality, okay? Something here might not affect what's going on here. Maybe it won't. But something out here can't affect what's going on here because influences can't move faster than the speed of light. Now, this diagram I've shown is for special relativity where there is no gravity. So if we now put in gravity and we apply this to the case of an expanding universe, the diagram looks like this. There's a lot of paraphernalia on this diagram, so just ignore anything from there up, okay? This is that past light cone again. Now, it looks kind of similar. What is different about this diagram is that this time axis, we've had to mess with it a bit. So this is not time, this isn't like 1 second, 2 seconds, 3 seconds. It's not uniform. We rescale and mess with the axis in clever ways so that the light cone is still nice and at 45 degrees. So here is the problem. This point represents a particular point on the cosmic microwave background in a particular direction, okay? We look out, the photon was emitted here, travels across and enters our telescopes, okay? This point represents the complete opposite point, that point over there, okay? On the standard cosmology, we can calculate what the past light cones of those points are. So these points here are all the space-time events that could possibly influence Q. And these ones are all the space-time events that could possibly influence P. And there is no overlap, okay? All of the causes that went into setting the temperature here and all of the causes that went into set the temperature there are completely different. And yet, those 2 points manage to be at the same temperature to 1 part in 10 to the 5. You see the problem here? It's not, if you want to say, okay, that's just initial conditions, that's how the universe started off, fantastic. That's fine. This is not really a scientific problem. Our model is doing just fine, but it's just a bit awkward. Usually, the gas in this part of the room and the gas in that part of the room are at roughly the same temperature because they've had time to reach the same temperature, okay? Ordinary, if you put a hot coffee down in a room, it will eventually, everything will come to the same temperature just via ordinary thermal interactions. So, 2 things having the same temperature looks suspiciously like that, and yet it can't possibly have happened in the standard model. Again, this is just a little bit awkward. It's actually worse. If you look at a point in the cosmic microwave background, how far away before you find a region where these 2 light cones don't overlap? And it's only 1 degree. Okay, so if this model were true, every sort of degree, every square degree on the sky would be a separate, pick a number between 1 and 100,000 and the whole sky pick the same number, right? It's just a bit awkward. We'd like something a little bit better than that. If you talk to cosmologists who were working in the 80s, this was early 80s when inflation first started, this was a real noodle scratcher, to quote Ned Flanders. There's another problem, the Monopole Problem. It would be less known except that this was the problem that actually started the whole business off. If you take a magnet, north and south end, in just an ordinary magnet, and you cut it in half, you don't get a south pole and a north pole. What you get is 2 little magnets. The reason for that is that the magnetic field is actually being created by charges in motion, and they can't create just one type of magnetic pole. In a lot of high energy particle physics theories, they predict that there is actually such thing as a magnetic monopole, as just a north pole with no south pole attached. Now, the problem with those theories was that if you then put them in a cosmological constant, they predicted that we should see those things in huge numbers in the universe, ridiculously high numbers, if standard cosmology is right. So that actually is a standard scientific problem. There is something wrong with our theories if these theories are correct. So the proposal that was put forward in the early 80s by a number of scientists was called cosmic inflation. And the idea is simply that in the very early universe, the very, very early universe, 10 to the minus 35 seconds, something ridiculously early, there was a very short phase in the history of the universe where instead of the expansion doing a decelerating expansion where it curves that way. It accelerated, so it curved that way. And it only needs to last a very short period, 10 to the minus 36 seconds, something like that. What that will do for you, ignore the diagram for a moment, what it does is it makes flatness now not something that the universe evolves away from, but something that it evolves towards. So I guess an analogy would be if I hold this stick like this, it's an unstable equilibrium, and I have to work hard to keep the stick vertical. But if I hold it on the other end, if it goes slightly to one side, it will get worse and worse and worse. Okay, but if I hold it at the other end, and I'm off to one side, things just get better and better and better. Okay, so an accelerating expansion does that sort of thing. It will drive you towards omega equals 1, towards flatness rather than away from it. In terms of the horizon problem, okay, the old diagram we had was basically everything from here up. What inflation does is it puts in a very short period of time, it puts a lot of space into this axis, so that these 2 points, their path light cones now intersect. Even though it was such a small period of time, there's so much expansion there. I mean, if you like, it can take a small region which is in thermal equilibrium and expand it so much that it looks like it was never in thermal equilibrium. But it's finally the monopole problem. What we need to understand here is something called reheating. During inflation, if you make the universe expand exponentially, it dilutes exponentially. So you take, if the universe expands, all the matter just sort of thins out. And if you do a lot of expansion, as you need to solve the other problems, you basically empty out the universe. So at some point, you need to fill it up again. So the temperature of the universe drops rapidly during inflation. Then you need to do something else to make it rise back up again. If you make monopoles before inflation, and then when you reheat the universe, you don't make them again, then you've solved your problem. Okay? All the monopoles that were made before inflation just get blasted out into the universe, and there's sort of one every observable universe, so there's not really a problem there. And then if you don't make any more after inflation, you don't refill the universe with all these monopoles. These were the sort of the driving force behind inflation. Something got thrown in for free, something that no one really sort of expected, was that inflation actually sets up the initial spectrum of perturbations in the universe. Now, let me try to explain what's going on here. Yeah, this explains itself, really. We can think of suppose you had, suppose the temperature in this room was different at different parts of the room. So it was very hot here, it was very cold here. We can think of that, the field of that in this room as being sort of decomposed into a series of sort of waves of hot and cold. If you're familiar with Fourier theory, that would be fantastic at this point, and if not, never mind. So that this sort of, we can decompose this, so this is a hot bit and then a cold bit and then a hot, and a really hot bit and a cold bit. We can decompose this into, this is just sort of these three waves. It's just, it's a mathematical trick, basically. What inflation predicted was that these sorts of perturbations would be Gaussian, which means that the probability of whether you get a more dense bit or a less dense bit follows like a bell curve or a bell curve. There's a very specific prediction for that. They would also be adiabatic. What that means is that the matter and the radiation are perturbed together. So you don't just have sort of, there's radiation filling the universe uniformly and then the matter just clumps together. Adiabatic, they clump together. So if there's more matter than average here, there will be more radiation than average here as well. That's a specific prediction, and that actually turns out to be right. and also what's called nearly scale invariant. In this case, you see the height of the waves in each case I've put together are the same, but there could be a sort of mix of heights. Okay, so if I made the really long wavelengths really big and the short wavelengths really small, then I'd get something like this where you can still see it's the long wavelength which is doing most of it, and then the small wavelengths just put a little bit of a bump on top. Doing it the other way, you can have really small long wavelengths and then really big short wavelengths, and you get something like this. The exact mix of short and long wavelengths, called the power spectrum, inflation gives quite a specific prediction of that, and that turns out to be actually quite well borne out by observations as well, which was is actually quite an achievement for inflation. That was not expected. The model was not, that wasn't even in anyone's mind when they were building the model. They then just said, okay, what would happen, and then it kind of worked. So I've said what happens with inflation, but I haven't said what actually causes inflation. And there's an important point to be made here. I'll get to the diagram in a second. Inflation is an effect, not a cause. As inflation is usually defined, it's something that happens to the universe. It's not a theory about what the universe is made of. It's something that if this happened, it would be really nice. And now we have to try and work out what actually did it, if it happened at all. In that case, inflation is kind of a bit suspicious. So a lot of most cosmologists, I think, are impressed by the fact that it predicts, some very impressive facts about our universe. But there's still a bit of suspicion there because there's no physics there. We don't know what it is. So you can build a physical model that kind of works. Now, here's a rough idea of what's going on. We have a form of energy which is a field. Now, the important thing about the field is that it has what's called a potential. Now, this is a little bit difficult to explain, but suppose that, again, we represented this axis here as the temperature in this room, the average temperature in this room. We could then model the change in the temperature with time via as if it was a ball rolling along this kind of slope, basically. This is the shape of the potential. So this could be sort of now when the temperature is about as hot as it gets, but as the sun sets, the temperature starts to drop. Remember, the temperature is this axis. And then, 9 p.m., it sort of levels out, and then we get to our coldest point at about 4 in the morning, and then dawn starts, and it starts to heat back up again, and then at this time tomorrow we're back in this stage. So this is a model where the temperature in this room is sort of analogous to a ball rolling in a potential, okay? So we do the same thing with the field, okay? So the energy in the field is modeled. So the value of the field, basically the energy in the field is modeled as a ball rolling in a potential. Okay, this is weird stuff, but stick with me here. There's an extra force. The expansion of the universe makes it as if this was had a lot of friction on the slope, so it rolled down really slowly. So the slope is muddy, something like that. So in the simplest form of this, for reasons that I try to think how to explain without using maths, but I can't think of it anyway. If the ball is rolling slowly, then that form of energy will cause the universe to inflate. So it will cause a period of inflation. Okay? Inflation will stop when the ball gets to the bottom of the well, and it will oscillate. So sort of think of a ball sort of in that oscillation stage. If the field is coupled to ordinary matter and radiation, it will put its energy in those forms and it will reheat the universe in that way. Now, once that is done, then we get the results of the standard model, basically. And the standard model, just normal expansion of the universe, but it's nearly flat and the horizon problem is solved and we've got perturbations and all the wonders of inflation are ours, okay? They're not a monopole in sight, okay? This is one model of inflation. There are other models. In particular, the shape of the potential is something we are literally just pulling out of nowhere. We just go, okay, that one's kind of nice. You could have another shape if you like. Let's have a quick think about what inflation needs to do in order to solve these problems. Okay, and there are more or less 6 things. First of all, there must be an inflaton field. There must be some form of energy which will do this. All right. For all this not to be just hypothetical, there needs to be a form of inflation, form of energy out there which can make the universe expand exponentially. Now, initially it was hoped that that would actually be the Higgs field, which would have been fantastic, but it's not. All right. So we don't know what it is. It's never shown up in any particle accelerator. There's no direct evidence of it. All it does is it does nice things with the universe, so we hope it's there. Number 2, inflation has to start. So there must be at some point when this form of energy takes control of the expansion of the universe. Okay? Remember the meat grinder? What you put in is what the universe is made of, and what comes out is how it expands. Eventually, the dominant thing going in must be this inflation field, whatever it is. Inflation must last. If inflation makes the universe twice as big and then that's it, that won't work. Generally, you must make it, it's called E-folding. Remember E? We're back at E again. In a fixed period of time, the size of the universe gets bigger by E. We need about 70 of those times, 60 or 70, in order for inflation to actually solve the flatness problem. Otherwise, it's useless. Right? Inflation must end. If the universe keeps inflating forever, then it's got rid of all the matter in every sort of observable bit of the universe. So if it never ends, then nothing ever happens. Interesting, right? We have to stop. When it stops, it must put all of its energy back into ordinary matter. Right? If the universe reheated with just pure radiation, that would be no good. Radiation doesn't, if it's too low in temperature, it won't do anything. Finally, you have to set up the right density perturbations. You remember from last well, you might remember from last lecture. If Q is too large, if the scale of the perturbations, how big the clumps are to start off with, is too big, you don't end up making galaxies. You make galaxies that are so dense they won't have planets in them, or you just make black holes. So inflation has a lot to do. One of the problems with inflation is that its predictions are basically in 2 forms. There are generic predictions where any type of exponential expansion will solve, say, the flatness problem and the horizon problem. Those ones are fine, but again, they're not. There's possible there could be some other sort of solution. Whenever inflation makes a really specific prediction, it's not necessarily unique. It will depend on exactly how you made the shape of the potential. But let me, very quickly, for inflation to start, this is a nice paper by, a nice paper by Tegmark called "What Does Inflation Really Predict?" I'll skip that one. One of the points of inflation that I might come back to is this line here, the success rate. So what he did was consider just a range of, like this, just sort of a whole landscape of different sort of wells that the inflaton could fall in and out of. What he found was this is the success rate where you get the right sort of inflation, where inflation ends, all those 6 things where it actually works, as a function of what parameters you put in to inflation. What you notice is this peaks at about 0.1%. So inflation in and of itself, how to say this? Even if you have the inflaton field, it can still fail to actually do the right things to the universe to make it feasible, to make a nice universe. There's another question of whether, you remember the entropy problem, 10 to the 10 to the 123 Penrose, and that picture of the creator with a little pin picking out that point. It's often said that inflation can solve the entropy problem. There is a lot of confusion in the literature about this. There's a lot of views one way or the other, and it's not really something I can give you a definitive answer to. The thought is that during inflation, the universe will be driven towards homogeneous and isotropic state. Remember, that's what was so special. Remember, the universe starts off really nice and smooth and homogeneous, and then black holes form and it gets all clumpy, and then this universe, when it ends, is just a mess of clumps and black holes. If inflation can set up the sort of special starting conditions, then it would seem to have solved the entropy problem. The problem with all sorts of ideas like this is, is the solution more fine-tuned, still fine-tuned? And I think this is my personal opinion. The calculations done in the literature, which seem to me to be the most secure, all come back with the answer that a field which can cause inflation is itself quite special. It is not a generic thing. So if this is the special state, but inflation can make this, but inflation itself is pretty special, we might have improved the problem a bit, but it's not really solved. So again, that's not. Oops, sorry. That is an issue of contention, and one that I don't think has fully been resolved as yet. How does inflation make a multiverse? Well, if we think of this as just sort of classical ball, and the whole universe follows the evolution of this bit, then the whole universe undergoes inflation and then stops inflation, and then we have the whole universe, doing sort of normal expansion. However, these are quantum fields, so what you shouldn't think of sort of a classical ball rolling down, but sort of more like a patch of slime just sort of spreading out over the roof. Some of that slime, so suppose this was very, very flat, some of it would, by chance, if you get the initial conditions right, ooze up the hill a bit. Okay, so let's start with a region of space, and then let it inflate for one e-folding time. So it's E bigger this way and E bigger that way and E bigger this way, though E cubed is about 20. We can think of that then as sort of 20 separate sections. Now, by chance, if things are set up right, one of those sections might have evolved up the hill a bit. What that means is, while 19 of them are just sort of rolling down the hill towards sort of reheating and just normal universe, Big Bang, post-Big Bang universes, one of those 20 keeps inflating. And because it keeps inflating, it creates a bigger part of the universe, right? That one sort of little region that didn't follow the rest of the universe down to reheating, but it kept inflating. It then inflates, right? It just keeps getting bigger, and so one little bit of that new region itself will go up the slope and keep inflating. So the idea here is that inflation will make different parts of the universe. Sorry, let me say this right. Inflation will always continue at some point in the universe. Okay, if it's not a stochastic, if it's not a definite thing, whether you will go down the hill or up the hill, then by chance enough bits of the universe will keep going uphill for a little bit of time, so that some part of the universe keeps on inflating. Now, there are certain conditions on this to say whether this will work or not. But once it starts, you are on your way to a multiverse. But we're not quite there yet, because we've changed the cosmological parameters, but we haven't messed with the parameters, the ordinary parameters of physics, the masses of the particles. So the thought there is that if There's something called spontaneous symmetry breaking. I won't go into this in any great detail, but it is at least plausible that as the universe reheats, it will not only just create a whole load of new particles, but actually it will pick the parameters of physics in a sense at random from a certain set of values. So that is basically the inflationary multiverse. Let me give a few brief words of comment. The first question you've got to ask is this a fairy story? Is this, all of these other regions of the universe are in principle unobservable, not just in practice. It's not a technological issue. We will never observe them. Now, in science, that's end of game, right? That's game over. We can't observe these. If you're not doing something observable, then go to the philosophy department. Couldn't resist. Sorry. This is not quite true, though. A good example is black holes. General relativity predicts that we will never know what's going on inside a black hole unless you jump in which case you can't get out to publish the paper about what you found about when you jumped in. So in principle, it's not possible to know. So why do we think we know what's going on inside a black hole? Well, that's simply because we have a theory of general relativity. We've tested it against all of its competitors, and it's performed very well. And that theory comprehensively and robustly predicts black holes and what their properties are. In that case, it's indirect, but it's at least plausible. I think most physicists would say, the evidence leads me towards GR, and GR leads me to believe I know what's going on inside a black hole. And so there is at least indirect evidence. Now, it would be lovely if that sort of scenario was true of the multiverse. I can't put this point any better than George Ellis did, so I'm just going to read you out a quote now. Here we go. Okay. The multiverse is implied by some forms of inflation, but not others. Inflation is not yet a well-defined theory, and chaotic inflation, which is the version I told you about, is just one variant of it. For example, inflation in a small closed universe fits all the observations without requiring a multiverse. In any case, the key physics involved in chaotic inflation, Coleman-de Lucca tunneling, which is kind of what I said, the sludge going back up the hill, sort of, is extrapolated from known and tested physics to quite different regimes. That extrapolation is unverified and indeed unverifiable. The physics is hypothetical rather than tested. We are being told that what we have is known physics predicting a multiverse. The real situation is that known physics is being extrapolated to hypothetical physics, which then implies a multiverse. And the first step, this step, involves a major extrapolation which may or may not be correct. So I personally think that is spot on. These are at least very interesting ideas. There is kind of a way you can test the predictions of a multiverse. It's not completely hopeless. You're not just brute force positing things out there. A good example of this is some of you may have heard of what's known as the firing squad analogy, which is by John Leslie, where he says, suppose you're facing a firing squad. There's 100 guys. The probability that they'll miss is 1 in 100. Ready, aim, fire, and you're still alive afterwards. Now, that suggests two ideas. One of them is they'd be doing an awful lot of executions, and they were bound to miss someone sooner or later, and it's only that person who would then be there afterwards to go, wow, I'm alive, right? There's no one there going, well, they all got me. Okay? The second hypothesis is someone's paid them all off and they've all missed deliberately. Now, what you can do, this is slightly extending the analogy, you can actually, by examining where the bullets hit, get some idea of which of those hypotheses is true. So a typical, if you were perfectly circular, Yeah, there's a physics joke about spherical cows, which I will tell you about over a beer. A typical 100 guys shooting might look like this. So, 1 in 100 chance of missing, so actually in this case one of the guys did actually miss. Now, if you make the hypothesis that they all missed by chance, they were all aiming for the center, but just by chance they all missed, you get a collection of bullets that looks like this. I actually did these calculations. It's a two-dimensional Gaussian if you're interested. Okay? If, on the other hand, you assume that they all missed on purpose, they have to aim off to the side a bit. And so that actually looks like this, where again, these are simulations. But the point of this is not really this one, it's this one. That this is what's called the Principle of Mediocrity, which is a great name. That under the hypothesis that they were aiming for the center of the target and they all just happened to miss, this situation is more special than it needs to be because they're too far away, right? This is what you would typically expect, but the fact that you're alive afterwards gets all of these points outside, but no further. There's no reason for them to miss by that much. Okay, so there's actually a very good case. I'm rapidly running out of time, but let's just power on. This is Ludwig Boltzmann. He had a fantastic idea. There's a wonderful paper of his in 1895. He's thinking about the second law of thermodynamics. He's thinking about entropy. And what?
I have a question.
Yeah, go for it.
If the sharpshooters had perfect aim,
I'm assuming they haven't got perfect aim because they missed 1 in 100.
oh, okay, but in the God case, he would need to aim a little bit off.
Yeah. That's where this analogy breaks down. My point is that this case, the multiverse case, predicts a certain distribution for these points. If you observe this, you might, is it God, is it this or that or the other? You can at least rule out the multiverse on this case. What hypothesis you think is true, meh. Okay, let me put this into practice. So, why is our universe so far from equilibrium? Now, Boltzmann, working in 1895, he thinks, okay, maybe what's going on is this. If the universe were infinitely old, and if the universe always just goes towards thermal equilibrium, towards maximum entropy, then it would be complete thermal equilibrium everywhere. But what if the universe as a whole is like that, but every now and then, just by chance, parts of it would fluctuate into being more ordered. Now that would be ridiculously unlikely, but life could only exist in those regions. Life can't exist in regions of thermal equilibrium. So his idea was then, maybe the universe as a whole is like that, and we just happen to exist in one of those fluctuations. Now, this is a fantastically good idea. The Boltzmann was ridiculously far ahead of his time. He's one of the greats of physics. There is a problem, or there's more than one problem. The situation would be gravitationally unstable. But, putting that aside, the problem is just like in the other problem. We observe a universe in which the bit we observe to be out of thermal equilibrium is huge, okay? Whereas if you're waiting around for a bit of the universe to fluctuate out of thermal equilibrium, every bit of the universe you have to wait for, it gets worse exponentially. So if there's a certain probability in a given time that this bit will fluctuate to a special state, and we'll wait for this, what's the probability that this bit and this bit, if you remember probabilities from high school, you multiply the probabilities. So if that's a small number times a small number. So every little bit of volume that you add is just getting worse and worse and worse, exponentially worse. The problem then is that if you did in Boltzmann's universe, if you went around with your clipboard to everyone in that universe and went, so how big is this region of thermal non-equilibrium that you're in? All of them would be in the smallest region possible that allows for their existence, because there's no reason for it to be bigger, right? Remember, these points were too special. They're too far away. So a big universe would just be special but for no reason. You wouldn't need somewhere that big. And so this kind of idea is actually a reasonably strong test of the multiverse. Let me skip ahead. I'm rapidly running out of time. You can use this kind of idea to predict the value of the cosmological constant. So what would we, if there were different values of the cosmological constant in different parts of the universe, well, in most of those it would either be, ridiculously big and no structure would form, or ridiculously small and it would make the universe just recollapse very quickly. In the middle somewhere we would expect to find ourselves, just observing a universe with a moderate sort of cosmological constant. That kind of prediction kind of works actually in our universe, because it was made before we knew that there is a cosmological constant in our universe, and it got the number reasonably right. So that kind of thing can go right. It can also go remarkably wrong with something called the Coolness Problem. So think about, there's two regions of space both inflating, okay? And now at a particular time, this region stops and becomes an ordinary hot Big Bang. This region waits another second, and then it becomes, it spawns Big Bangs. In that extra second, this guy inflates much, much more, okay? So there's then a playoff, okay? This guy started making life earlier. He had a bit of a head start, but this guy was a lot bigger, so he made a lot more universes, so a lot more chances to make life, but they didn't have as long for it to make life. And what wins in this situation is region B, because the inflation happens so quickly. An extra second will get you sort of 10 to the 38 more universes. What that means is, for every, if this kind of scenario was right, for every universe which was as old as ours, there would be about 10 to the 38 which were 1 second younger. Now, that's a problem, right? Because that sort of multiverse would predict that we would be in the youngest universe capable of producing life, that we would be freakishly early, we would have evolved freakishly early in our universe, because those types of observers are so much more common than guys like us who just waited around for 13 billion years for it all to happen. This is called the Coolness Problem. The catch is a very small thing. I said now, but actually general relativity, as you may know, time is relative. So saying that I'm going to look at all, across the whole universe now is not well defined. Certainly, different observers could decide they wanted to slice space up differently in terms of space and time. What that raises is what's called the measure problem. You need some way of predicting what's going on in these universes. And as George Ellis points out, if you're going to make a multiverse proposal, where are you going to get the measure from? I mean, you have to get it from somewhere, and how on earth is that going to be a scientific postulate? Where how are you going to do an observation that tells you how many different types of each sort of universe you create? How much time have I got? I think I'm over time. Oh, I have 2 slides.
Yeah, just finish.
Okay.
5 more minutes.
The Boltzmann problem, the problem that our universe is too big, is actually a problem that comes back to bite the inflationary universe. Again, I can't put this any better than this is Roger Penrose. Let me just pull out the, this is a lot of reading, I know. Let me pull out the important bits. Do we need the whole observable universe in order for sentient life to come about? This seems unlikely. It would be hard to imagine that even anything outside our galaxy would be needed. Let's be very, very generous and ask that a region 1/10 of the size of our observable universe must resemble the universe we know. Now, if you now think, okay, I have a region of space that's going to blow up to be the size of our universe, and I have another region of space that blows up to be just 1/10 the size of our universe. If those smaller universes are more likely, and in the sort of Boltzmann scenario they are, because there's for entropy reasons, we can estimate how much more frequency the creator comes across. He's using creator here in general terms. You just never mind. It comes across as the smaller regions and the larger regions. The figure is no better than, here's that number again, 10 to the 10 to the 123. You can see what an incredible extravagance it was in terms of probability for the creator to produce that extra bit of the universe which doesn't affect us at all, but is still a low entropy part of the universe that we don't actually need for our existence. So there are, I think, let me give the moral of the story here. The moral of the story is that sometimes faced with the fine-tuning of the universe, people think they can just go multiverse, job done, right? There's a lot more you've got to do, and multiverses are not easy things to make and make properly. You've got a lot of issues that you need to sort out. What exactly does the multiverse predict? They can, as the Coolness Problem and as the Boltzmann multiverse explains, they can go catastrophically wrong. Now, that sort of testing is sort of consistency testing. It's not normal scientific direct observation, but it can in fact be quite powerful. So that is one example of a multiverse and some of the problems that go in it. There are a couple of other ones which I'll just mention if you want me to chat about them afterwards. Quantum mechanics, there's one interpretation of quantum mechanics which says that whenever whenever a system has to make a quantum decision, the universe actually splits in two. That is exactly as weird as it sounds, and I don't understand what's going on. Smolin has a very interesting style of multiverse where in the center of black holes, for reasons I do not even begin to understand, that universes could be born in the center of black holes. What then, you get a sort of Darwinian situation where if you make, suppose you have two black holes. The properties of this universe are randomly sort of sit around. If that universe happens to make more black holes, it will tend to make more universes that inherit its own properties. It's an interesting idea. I am in absolutely no position to give you any sort of position on that. Finally, the word you're all looking forward to. Harrison's intelligent model. Edward Harrison is a very good cosmologist. He had this idea, if you could simulate a new universe, if you could make a new universe, if we could do that in a lab, we would want to try and make the sort of universes that were interesting, right? We wouldn't want to make boring ones that do nothing. We would want to make interesting universes. In particular, maybe we'd want to make universes which are capable of evolving life which itself is able to make universes, so that our universe would have descendants and children and grandchildren and great-grandchildren and so on and so forth. So in fact, most of the intelligent life that existed at any particular time would in fact be there because of intelligent design from the guys in the next universe up. It's an interesting idea for a start. I think I'll give this to you for my parting thought is that actually that provides a good thought experiment, because if you were in one of those universes, like it or lump it, intelligent design would be correct, at least for the next level up. Maybe not as a fundamental explanation. So it's an interesting thought experiment to think what would go wrong with all the critiques of the design argument in that universe. They would all, in fact, fail. So it would be a question then, well, what would actually be wrong with them? So that, I think, is a useful thought experiment for what is coming up in the next few days. And I'll leave it there. Thank you very much.